You know, when you look around at our world, the skyscrapers, the massive bridges, have you ever really stopped to think about what's holding it all together? There's this incredible, invisible architecture at work. And today, we're going to decode the blueprint of that hidden strength, reinforced cement concrete design. Let's get into it.
So we think of concrete as, well, concrete, right? It's the definition of tough. It's solid, permanent. But what if I told you it has this one huge, almost paradoxical weakness? A flaw so critical that if we hadn't solved it, our modern cities just wouldn't exist.
And here's that paradox right here. See, concrete is an absolute beast when it comes to compression. You can squeeze it, you can crush it with unbelievable force, but the second you try to pull it apart, what we call tension, it's surprisingly brittle. It just cracks.
So how do you solve a problem like that? Well, with a brilliant partnership. You bring in another material, steel. Because you see, steel loves tension. It's fantastic at handling those pulling forces. You put them together and you get this incredible composite material, a real superhero team that literally built the modern world.
All right, so here's our game plan for this explainer. We're going to start with that essential partnership. Then we'll decode the materials themselves. After that, we'll look at the whole evolution of design, get into the modern standard, understand its two pillars of safety, and then wrap up with the core assumptions that every single design today is built on. So yeah, the magic is really in this synergy. When you embed steel bars inside the concrete, you're creating a system where each material gets to do exactly what it's best at. The concrete takes all the crushing compression forces, and that steel skeleton on the inside, it handles all the pulling tension. Simple as that.
But, to really get how this team works, we got to get to know the players individually. I mean, what is concrete, really? And how does steel behave under all that pressure?
First up, concrete. It's not really one thing, it's more like a recipe. You've got cement, which is the glue, you have aggregates, sand and gravel that give it bulk and strength, and then water, which kicks off the whole chemical reaction. Now, for engineers to actually do their calculations, they have to simplify this. So they treat the final hardened product as if it's one single uniform material. And that assumption, it makes all the math possible.
Okay, so this graph, think of it like a personality profile for concrete when it's under pressure. As you apply more stress, it starts to deform or strain along that curve. But, and this is a big but, there's a hard limit. Once it deforms by just 0.35%, that's a strain of 0.0035, that's it. It's reached its breaking point. That number, 0.0035, is an absolutely non-negotiable limit in modern engineering. And here's the other half of our dream team, steel reinforcement, or what we call rebars. Now, you might see some plain bars out there, but the real workhorse today is something called a high-yield strength deformed bar, or HYSD for short. See those ridges on it? They're not just for looks. They're absolutely crucial for helping the steel grip the concrete, making sure they work together as one cohesive unit.
And check out steel's personality profile. It looks totally different from concrete's, right? Instead of being brittle, steel stretches, it yields. It has this long, elastic phase where it can deform a lot without breaking. And that quality, that ductility, is exactly what makes it the perfect partner to handle all the tension that concrete just can't.
So, we know the players, now let's talk about the playbook. Because designing with these materials isn't something we figured out overnight. Oh no. It's been a century-long evolution in thinking, moving from really cautious, simple rules to a deep, scientific understanding. And that journey, it really has three big chapters. We started with the working stress method, then we evolved to the ultimate load method, and finally we arrived where we are today with the most comprehensive approach, the limit state method.
The first approach, WSM, was, well, let's just say it was super cautious. The whole idea was that the stress in a structure should never go above a tiny fraction of what the material could actually handle. It was safe, for sure, but it was also pretty inefficient because you weren't using the full strength of the materials. Plus, it was all based on some wrong assumptions about how concrete actually behaves.
So to fix that inefficiency, engineers came up with the ultimate load method, ULM. And this was a huge leap. Instead of focusing on everyday loads, it focused on the ultimate load a structure could take just before it collapsed. This led to much more realistic, more economical designs. But it had its own massive blind spot. It didn't really care how the building performs day to day. Things like cracking or sagging weren't really part of the equation. And that brings us to the hero of our story, the modern standard that takes the best of both of those worlds and fixes their flaws, the limit state method.
So when the world is a limit state, it's actually a pretty simple idea. It's just any point where the structure stops doing its job properly. Now, that could mean a catastrophic collapse, sure, but it could also be something way more subtle, like a floor that bounces a little too much, or a beam that visibly sags.
And this is the absolute genius of the limit state method. It splits the whole design process into two separate checks. First, you have the limit state of collapse. That's all about safety, preventing total failure. And then you have the limit state of serviceability, which is all about making sure the building is actually usable and comfortable for its entire life.
So let's really dig into these two pillars, because this is where modern design gets so smart. It recognizes that a building that's safe but, is uncomfortable or cracks all the time, that's not a successful design.
Pillar number 1, collapse, is the ultimate safety check. Engineers have to consider every possible way a structure could fail, by bending too much, by being crushed, by shearing apart, or by twisting. The goal here is brutally simple. Make sure it will not fall down, period.
Then you have pillar number 2, serviceability. And this is all about performance and how it feels to actually use the building. This makes sure that floors don't sag in a way that makes people nervous, that any cracks are kept to a harmless microscopic width, and that the building doesn't have any weird, uncomfortable vibrations. It's about making sure the structure is durable and just a good place to be.
Okay, so with this really sophisticated two-part approach in mind, what are the final absolute rules of the road? Well, it all boils down to just a handful of core assumptions that create the mathematical foundation for every single modern design. It all comes down to these fundamental ideas. These are the rules everyone agrees on so the math actually works. For instance, they assume that a perfectly flat slice of a beam stays flat, even after it bends. They make big, important simplifications, like pretending concrete has zero strength and tension, and just letting the steel handle that entire job. And of course, they follow those hard limits we talked about, like that maximum concrete strain of 0.0035. That's the point of no return.
And as the source material puts it so perfectly, these principles combine to form a robust framework that balances safety, collapse, with performance, serviceability. And that right there, that elegant balance, that is what modern structural engineering is all about.
So the next time you're walking through a city and you look up at a skyscraper or drive over a huge bridge, you're not just seeing concrete and steel. You're seeing a century of evolving philosophy right there in front of you, a silent, powerful partnership between two amazing materials, governed by a design code that's thinking not just about your safety, but about your comfort too. What hidden forces will you see now?